Good morning, good afternoon, good evening. This is video 7 of STAT 248, Couplings in Monte Carlo. In this video, we are looking at examples of geometric ergodicity for different Markov chains. And this corresponds to the last part of the chapter 3 of the lecture notes. So far, we've looked at Markov chains denoted by xt, with initial distribution pi 0 and transition kernel denoted by capital K. And in particular, in this chapter 3 of the lecture notes, we've looked at geometric ergodicity. That is, obtaining an upper bound on the distance between the teeth distribution of the chain pi t and pi of the form c times rho to the power t, where rho is called the rate, is a value between 0 and 1. C is a finite constant. The distance itself is TV or Wasserstein, for example. And C, the constant, might depend on the initial distribution of the chain. And the question is how to obtain such results. We've looked at different techniques, generic techniques to obtain such results. In particular, drift conditions, minorization condition, also contraction between chains, iterated random function, and so on. In this video, we will look at specific examples where we will try to obtain the rate and the constant in the geometric ergodicity result. In particular, AR1 processes, a Gibbs sampler for the Ising model, and quickly a Markov chain for the conditional Bernoulli distribution. So we will use some of the techniques seen before and also we'll see a few new techniques. We will start with the AR1 process. So we're going to assume that x0 is a normal with mean m0 and variance sigma 0 square. And then we write xt plus 1 as eta xt plus tau epsilon t plus 1, where the sequence of variable epsilon t are independent normal 0, 1 variables. So first, as we've seen before, we can find the invariant distribution of the Markov chain. So we write that xt, for example, if it was normal m sigma square, then at the next step, xt plus 1 would be marginally distributed as a normal with mean eta m, variance eta square sigma square plus tau square. And so if we wanted this distribution to be invariant, this would impose some conditions on m and sigma square as a function of eta and tau. In particular, from the means, we obtain that m equal eta m is only true when eta is non-zero if m is exactly 0. And on the variances, the conditions lead to sigma square must be tau square divided by 1 minus eta square. And thus the invariant distribution of the Markov chain is this normal m sigma square with those m and sigma square. So the geometric ergodicity question is how quickly does the chain converge to this stable invariant distribution? So the coupling approach for this question consists in considering x tilde t, which is another Markov chain with the same Markov kernel. So here actually the Markov kernel can be written explicitly. The density of kx x prime is the normal density evaluated at x prime with mean eta x and variance tau square. And x tilde will be assumed to be at stationarity. So we start x tilde at stationarity. And thus it remains, of course, at stationarity. And so x tilde t for all t is distributed as this normal distribution with mean m and invariant sigma square. So a very simple approach for geometric ergodicity here consists in using contractions. And so, in fact, simply using common random numbers, we can write the evolution of two chains when provided with the same epsilons. So we use the same epsilon t plus 1 at time t plus 1 to generate both x t plus 1 and x tilde t plus 1. And by induction, we can compute that the expected distance between two chains using this common random numbers coupling is less than eta to the t times the expected distance at time 0. This directly leads to an upper bound on the one Wasserstein distance between pi t and pi, which we can write W1 of pi t and pi, or in a norm notation. By definition, this is an infimum over all couplings of pi t and pi of the expected distance between x and x tilde when x tilde follow this coupling gamma of pi t and pi. And so if we consider any particular coupling, we find that this infimum is less than the expected distance between xt and x tilde t under any particular coupling. And so in particular, for the coupling considered here, the common random numbers coupling, we obtained an upper bound of the form eta to the t expected distance at time 0. And so we obtain basically geometric ergodicity in Wasserstein 1 with the rate eta. The autoregressive coefficient turns out to be the geometric rate of convergence in the Wasserstein 1 distance. And the constant depends on the initial condition. And of course, via x tilde 0, it also depends on the invariant distribution sigma square and m. So a question at this point is, can we obtain a similar result in total variation? So we will talk briefly about a little tool to convert Wasserstein bounds into total variation bounds. And that is from a paper in 2010 by Madras and Setzer. So we will recall a few things. So first, the marginal distribution at step t, pi t, has density written pi t minus 1k, defined as an integral over the previous step pi t minus 1 of dx times k of x prime. So that's the density at step t. And we'll recall also a certain characterization of the total variation distance as half of the area between the two PDF curves. So equipped with those reminders, we will consider the total variation distance between pi t and pi. Pi is the invariant distribution. We write this in terms of the kernel as pi t minus 1k minus pi k. And of course, here we use the fact that k is pi invariant, so pi is equal to pi k. Using the representation of the total variation recalled above, we see that this is half of the area between the two PDF curves. And then we write what those PDFs are in terms of the previous, as integrals in terms of the previous step pi t minus 1 and the transition kernel k. So we get a lot of integrals now. We have 3 integrals in this expression. 1 over x prime, which is the next step. 1 over x, which is the distribution of the chain at step t minus 1. And 1 over x tilde, the stationary distribution. And so we realize that this difference between two integrals can be written as an integral of a difference where we write the integral over x and x tilde of the difference between k xx prime and k x tilde x prime with respect to a joint distribution gamma over x and x tilde, where this gamma is in fact any joint distribution with marginals pi t minus 1 and pi. So it's a coupling of pi t minus 1 and pi. And so having obtained this expression, we now employ an inequality. So we put the absolute value signs inside the integral, which is a triangular inequality. And we write 1/2 of a triple integral of the absolute value of the difference between the kernel densities with respect to the joint distribution gamma. And we recognize again the total variation distance between the distribution kx dot and the distribution kx tilde dot integrated over x and x tilde. So that's useful. Why? Because if we next assume that in fact this total variation distance between the two transitions conditioned on x and x tilde is less than some constant times the difference between x and x tilde, so it's some sort of again Lipschitz continuity between the transition densities, then we obtain that the total variation between pi t and pi is less than this constant, here denoted by zeta, times the expectation of the difference between x and x tilde under the coupling gamma, which is any coupling of pi t minus 1 and pi. So this works for any coupling gamma. And in particular, since this works for any coupling gamma, we can take the infimum over all couplings of this expected distance, and we obtain zeta times the 1 Wasserstein distance between pi t minus 1 and pi. And of course, this is what allows us to obtain a total variation upper bounds from a Wasserstein 1 upper bound. So if we are back in the context of autoregressive processes of order 1, we can see how this can pan out. If we manage to obtain the appropriate upper bound on the total variation distance between two transition kernels conditioned on different starting points. So for this, it will be convenient to write the total variation between those kernels in terms of 1 minus the pointwise minimum between the two transition densities integrated over the whole space. And of course, in the case of AR1, those transition densities are in fact normal densities with mean eta x and variance tau square. And so we can visualize this overlap. We can write the two transition densities centered at eta x and eta x tilde. And there's a midpoint. And the curve that is the pointwise minimum between the two normal densities has a certain integral. And we're looking at effectively lower bounding this integral to obtain an upper bound on the total variation distance under consideration. So in fact, we can compute quite precisely what this overlap area here is. And so we can see, for example, that this overlap is twice the tail probability of a normal. So we integrate from the midpoint to infinity a normal density centered at eta x, for example, or we could have chosen the other density and integrate from minus infinity to the midpoint. And we multiplied by 2 because this overlap area is the sum of two symmetric areas. And so this tail probability is the probability that a normal 0 tau square is more than the midpoint, which is eta x tilde minus eta x over 2. And this is twice the probability that a standard normal is above a certain value. And of course, that we can write in terms of the normal CDF. So we can write twice 1 minus the normal CDF evaluated at eta times x tilde minus x absolute value divided by 2 times tau. Okay, we now deal with familiar objects, so there are some calculations that we can do to obtain sort of more explicit bounds on those quantities. And in particular, we can obtain an upper bound on the normal CDF. So phi of A is always less than 1/2 plus A divided by square root of 2 pi when A is strictly larger than 0 or equal to 0, in fact. That's because the area up to 0 is equal to 1/2, and then the area from 0 to A is less than A times the maximal of the density, which is attained at 0, and it's equal to 1 over square root of 2 pi at 0. That leads to an upper bound of the form eta times the difference between x tilde and x divided by square root of 2 pi times tau. And so indeed, the total variation distance between those two kernels is bounded by a constant times the difference between x and x tilde. Therefore, we can apply the previous result, which leads to the total variation distance between pi t and pi being less than eta divided by square root of 2 pi tau multiplied by the Wasserstein 1 distance between pi t minus 1 and pi, which we have obtained before. And so we can copy the previous bound. The previous bound on this 1 Wasserstein distance was the expected distance between x0 and x tilde t0 at time 0 times eta to the t minus 1. So overall, we obtain this geometric ergodicity result in total variation this time. And so the rate is still eta, and the constant here can be finite, depending on our initial distribution assumption. So you can note that the constant, in fact, so this c here, which is depends on the initial distribution, but also on tau, goes to infinity when tau goes to 0. In general. And that's not necessarily desirable. We can in fact obtain more accurate results where the bounds would not depend on tau in this way. And for this, I refer to a 2016 paper by Durmu and Moulin, who analyze unadjusted Langevin processes for log concave distribution, and this includes the AR1 process as a particular case. So next, we will look again at the AR1 process, but discussing whether drift and minorization conditions could be employed. And for this, I refer mostly to Charles Geyer's lecture notes on MCMC, section 3.7 in particular. So we're looking again at xt plus 1 equal eta xt plus tau epsilon t plus 1. And we will try to find a drift function for this Markov chain. And because this Markov chain is essentially Gaussian, it's easy to work with quadratic functions. And so we will try the function v of x equal 1 plus ax squared for some constant, positive constants a, because that's a function v that is certainly larger than 1 for all x. And we want drift functions to be functions larger than 1. And then we can compute the expected value of this function at the next step, given that the chain is currently at x. And again, since the Markov transition is Gaussian, we can compute this very explicitly. And we obtain 1 plus a times tau square plus eta square x square from the second moment of a Gaussian. And so we can expand this expression. We have some constant terms and terms that depend on x. So 1 plus a eta square x square plus a tau square. And we would like this to be of the form of a constant times v of x plus another constant. And so we write eta square v of x plus 1 minus eta square plus a tau square. And for v to be a drift function, recall that we want kv of x to be less than lambda v of x plus b, indicator that x is in a set C, where lambda is a constant less than 1, more than 0 and less than 1, b is a finite constant, and C is a set. And so here, in fact, we can indeed choose a lambda anywhere between eta square and 1. And then we can choose a value d such that the set C is defined as the set of x's such that v of x is less than d. We can find a lambda and a d such that indeed we can write kvx is less than lambda vx plus b, indicator that x is in C. And in fact, those sets here, the set C of this form, they can be equivalently seen as set C of x that have absolute value less than a certain value epsilon. Here, epsilon is not necessarily a small value. If d is large, then epsilon will be large. So we can indeed find a drift condition. And in terms of minorization condition, we would be looking at verifying the statement that for all x in a set C, the distribution kx dot is lower bounded by delta nu dot, where delta is a strictly positive value and nu is a probability measure. So if we consider set C of the form above, kx dot again is a normal centered at eta x and with variance tau square. And so indeed, if we choose nu to be, for example, the stationary distribution, we can in fact find a delta, a very small value, by taking the infimum of kx dot over the set C. Now the biggest issue when doing this approach is, on top of the calculations being quite tedious, is that we obtain a geometric ergodicity result with a rate rho that is very close to 1. And that doesn't come from the drift condition, that comes from the minorization condition. So in other words, whichever way you proceed, you will have to find delta to be an extremely small value. And in turn, this will result in rho being close to 1. I refer to Charles Geyer's lecture notes for the precise statements. Next, we look at a different example, the example of the Ising model. This was described in chapter 1 of the lecture notes, and here we'll look at the same model again. So recall we have a two-dimensional grid of spins that take value in -1 plus 1, or just minus and plus. So we can visualize a grid, for example, a 4x4 grid. And at every vertex in a grid, we have a plus or a minus, or +1 or -1. So here it's a 4x4 grid. And we define, so the state of the Markov chain is x is such a grid. And we define pi of x to be proportional to the exponential of some positive value beta times the sum over all neighboring vertices of the product of the spins at those neighboring vertices. So v prime refer to neighbors in the grid. So if we have a two-dimensional grid, here we have 4 neighbors for every element, every vertex in the grid. So the one above, below, on the right and on the left. So we have 4 neighbors per site. So the site or vertex is every element in among the n square elements in the grid. And we consider periodic boundaries, which means that if you consider a site that is on the boundary, so for example next to the right border or the bottom border of the square, its neighbors are retrieved from the opposite side. So you can copy the first leftmost columns to the right, or the first row at the bottom, to obtain the 4 neighbors of any site at the boundary. So the goal is to sample from the distribution pi, of course, and we will do this with Markov chains. And we consider beta to be fixed. Beta is referred to as the inverse temperature in this context. Beta is a fixed constant, and we will consider a Gibbs sampler. So starting from a grid X, we will choose a site V at random uniformly. So uniformly among the n square sites that compose the grid. And we will update the spin at that location V. So we will put a plus or a minus there. And we will do so by sampling from the conditional distribution of this spin xv given all the other spins. And we denote this conditional distribution by pi of xv given x minus v. X minus v refers to all the other sites, whereas xv is the variable corresponding to site v equal to plus or minus. So from the form of the distribution pi of x, we can in fact obtain the conditional distribution of xv. So we can compute the probability that xv should be plus 1 or minus 1 given the other sites according to the distribution pi. And this can be just from the base formula, so to speak, or the law of total probabilities. This is equal to pi of a grid x plus divided by pi of a grid x plus plus pi of a grid x minus, where x plus is x with a plus 1 at location v, and x minus is x with a minus 1 at location v. So just notation for this particular site v, we write x plus to be x, except that xv is replaced by plus 1, and x minus is like x everywhere except at location v, where we put a minus 1. So of course, it's very easy to sample xv by computing this probability and just sampling a Bernoulli random variable. And this probability, of course, simplifies here. We don't have to compute the sum over all the vertices. We can write exponential beta sv over exponential beta sv plus exponential minus beta sv, where sv is the sum of the neighbor of v. So there are 4 neighbors, so it's a sum over all the 4 neighbors of either plus 1s or minus 1s, depending on the state of the neighbors. So this will be equal to minus 4, minus 2, 0, plus 2, or plus 4. And so this expression can be further written 1 plus the hyperbolic tangent evaluated at beta sv divided by 2, where recall that the hyperbolic tangent of z is defined as exponential z minus z divided by exponential z plus exponential minus z. So this is simply a certain function of beta and of the sum of the neighbors. And this function hyperbolic tangent is a function that goes from minus 1 to plus 1 when z is any real value. But in fact here z will be only any of the 5 possibilities depending on the sum of the neighbors. So the strategy to obtain geometric ergodicity here will be, again, of course, to employ a coupling. And so we will consider our Markov chain xt evolving according to our Gibbs sampler. and another Markov chain, x tilde t, which is distributed according to pi. So it's at stationarity. It's already at the distribution pi, but it undergoes the same dynamics. So it moves according to the same Gibbs sampler marginally. So it's the same strategy as we did for the AR1 process. But here we will obtain an upper bound on the TV between pi t and pi using this so-called coupling inequality. So we write the probability that xt is different from x tilde t. And this is equal to the probability that the distance between xt and x tilde t is strictly more than 0. And for the distance between x and x tilde, we will count the number of locations v such that xv is different than x tilde v. Equivalently, this is 1/2 of the sum over all locations of the spins at location v in x and x tilde, because the difference, if there is one, is equal to 2 between -1 and +1. So this total variation distance between pi t and pi is less than the probability that the distance is more or equal than 1. And by Markov inequality, this is less than the expectation of the distance. So this is an application of Markov inequality, since the distance is a non-negative random variable. And so, of course, if we can prove next that this expected distance goes to 0 geometrically in time, and in particular, we would obtain this if we can prove that the expected distance over one step, so given the previous states, is less than multiplied by a constant lambda, where lambda is less than 1. Then, if that was the case for all grids at the previous step, so all x tilde at time t-1, then we would obtain by induction that the total variation distance between pi t and pi would be less than lambda to the t times the distance at time 0, either fixed if we fixed the states, or in expectation under some initial distribution and some in the stationary distribution. So we would obtain a geometric ergodicity result, but the issue is that it can be hard to obtain a contraction by a factor lambda, such as above, from any pair of states x tilde. So we would have to consider all states xt-1, x tilde t-1, and we would compute the expected distance over the next step. And considering all states is like taking the supremum of all the lambdas that we would obtain for every pair of states. And so there's a very convenient tool called path coupling, due to Bublé and Dyer, 1997, which state that, in fact, instead of considering all x and x tilde at time t-1, it is enough to obtain the contraction over one step. So again, the expected distance at the next step is less than lambda times the current distance. It is enough to obtain this contraction for all states that are at distance 1 to one another. So instead of considering all possible pair of states, we consider only the adjacent states xt-1, x tilde t-1, such that their distance is equal to 1. We do not need to consider the states that are further away than that. So let us see why the path coupling argument works. And it's an argument that works for the Ising model, but also in many other cases, discrete but also continuous. So let's consider x and x tilde that are in fact far away. So their distance is equal to capital D, say more than 2. We can construct, so that's an assumption, we can construct intermediate states denoted by Z that are adjacent to one another. So Z1, Z2 are at distance 1, Z2, Z3 also, and so on, in between X and X tilde. So if we can construct those Zs, and we can construct those Zs deterministically given X and X tilde, we will look at an example in the Ising case. Suppose we have simply n equals 3, we have 3 by 3 grids of spins. And so let's look at X. It's this grid of pluses and minuses. And we will create intermediate states linking X and X tilde. And X tilde is going to have 3 differences with X. So we're putting pluses and minuses, but 3 of those pins are different than in the grid X. They are circled here. And so then we can simply introduce those differences one by one to obtain Z1 and then Z2, so that the distance between X and Z1 is 1, the distance between Z1 and Z2 is 1, and the distance between Z2 and X tilde is also equal to 1. So since the total number of differences was 3, it was enough to introduce 2, which is D minus 1, intermediate states to obtain this sequence of states. So based on this sequence of states, we can generate X prime and X tilde prime at the next step. So this is doing one step of our Gibbs sampler here in the case of the Ising model, as follows. We generate them in a contractive coupling from adjacent states X and Z1 first. So we obtain X prime and Z prime 1. And we assume that we can find a contractive coupling to do that. So we assume that we have this contractive coupling, but that operates only when the states are adjacent. And we apply it to the successive states. So we generate Z2 prime from this contractive coupling, but we have already generated Z1 prime. So what we do is we sample from the conditional distribution under this contractive coupling. So given Z1 prime, and also the coupling is defined given Z1, Z2. And we do this all the way up to the generation of Z D minus 1 prime and then X tilde prime. So it's a construction that is going to only be used for theoretical purposes, but the consequence of this construction is that the expected distance between the generated states X prime and X tilde prime, by the triangle inequality, it's less than the expected distance between X prime Z1 prime plus the distance between Z1 prime, Z2 prime, and so on up to Z prime D minus 1 X tilde prime. So that's simply introducing the intermediate new states and applying the triangular inequality. And then by the linearity of the expectation and the fact that we have a contractive coupling from adjacent states, we have a lambda contraction in front of all of those distances. So now we have a sum of lambda times the distance between the successive states at the previous step. And of course, by definition of this sequence, this is equal to lambda times d, the distance between X and X tilde. This means that we can in fact obtain the contraction rate lambda from X and X tilde, even though they are not adjacent, but using this construction of a specific coupling. So it's enough to find a contraction rate from adjacent states. So now back to the Ising model. We consider adjacent grids, and we're going to find a coupling that produces contractions. And by the path coupling argument, it's enough to consider adjacent grids. We will obtain the same rate from non-adjacent grids with the path coupling construction. So let's look at grids that differ only by one spin, here circled. So it's just one location where x and x tilde differ. And we're going to employ a very simple coupling strategy of our Gibbs sampler. And we will have to compute the contraction rates. So there will be a bit of calculations. But we will see that the result will be that the chains contract with a certain rate lambda strictly less than 1. So here's the coupling. At every step, we will choose the same site, V, in the grid X and in the grid X tilde. So among all the n square sites. And then we will use a common random number strategy in order to generate the spins. So that is, we will use the same uniform and we will compare it to the probabilities of a plus or minus at location V in both X and X tilde. And if you recall from chapter 2, common random number couplings for Bernoulli variables is also the maximal coupling. So there's a maximal chance of obtaining the same spin in the grid X and in the grid X tilde at location V under the probabilities given by the target pi. So we will denote by S and S tilde the sums of the neighbors at location V. We drop V from the notation because everything from this point onwards will be at location V. So that's the site selected for this update. And then, so if the site V chosen is not a neighbor of the site at which the grids differ, so let's call this V star. V star is where X V star is different from X tilde V star. So if the chosen site is not close by, then the sums of the neighbors will be the same for both X and X tilde. So S is equal to S tilde. Because X and X tilde only differ at location V star. So if S and S tilde are the same, the probabilities for the spins at XV and X tilde V are the same. And so using the same random numbers, we will obtain the same spins again. If we choose to update specifically V star, which happens with probability 1 over n square, then in fact the neighbors are the same. And after the update, the difference between XV and X tilde V will be resolved. And so the distance will between the grids will become 0. It will decrease from 1 to 0. And finally, if we choose a neighbor of V star, so there are 4 neighbors among n square sites. So if we happen to choose one of those, then the difference between the sums of the neighbors is equal to 2 here. Because V star is one of the neighbors. And so it's possible that the update could increase the distance between the grids now. So it's possible that after the update, XV would be different than X tilde V. And that would happen with probability given by the difference between the probability of updating to a plus in the grid X and in the grid X tilde. And so overall, summing over all those possible cases and the resulting distances between the grids, we can in fact obtain that the expected distance at the next step will be less than a certain lambda times the current distance between the grids. And of course, we're looking at adjacent grids, so the current distance between the grids is equal to 1. So skipping the calculations, the resulting lambda for the two-dimensional grid is of the form 1 minus twice the hyperbolic tangent at 2 beta divided by n square. So n square is the number of sites in the grid, and beta is the inverse temperature associated with the target distribution pi. So altogether, this leads to a geometric ergodicity result in total variation with a rate equal to this rate lambda. So this quantity, which of course we want to be less than 1. And the constant is the distance between initial states. And of course, the worst case scenario is that the initial distance is n square. That's the maximal possible distance, and so we can always replace this by n square. So at the end of the day, we obtain an upper bound which is quite explicit in terms of n, the size of the grid, but also in terms of beta, the inverse temperature. So recall, of course, it's again only useful if the rate is less than 1. If the rate was more than 1, the upper bound would explode and we would not learn anything because the TV is always less than 1. And here this means that we want 1 minus twice the hyperbolic tangent of 2 beta to be more than 0. And so we can sort of massage this expression. And basically what it means is that beta must be small enough, or the temperature must be high enough for this upper bound to be meaningful, to be non-vacuous or non-trivial. So if you were interested in the case of low temperature, which is obviously interesting as well, you might have to employ a different strategy. But this coupling strategy seems to provide non-trivial results, at least for high temperatures. And so, of course, once we have this upper bound on the total variation distance, we can find the so-called mixing time, or an epsilon mixing time, or at least an upper bound on it. And so what does it mean? For example, we might want to know what is the minimal time at which we have the guarantee that the total variation between pi t and pi is less than epsilon. And so that would be the case if our upper bound was less than epsilon. So we can write our upper bound as 1 minus a constant that depends on beta divided by n squared to the t times n squared. And so then we can do a bunch of manipulations if we would like to see what it would mean for t as a function of epsilon, n, and beta. So without losing anything, for example, we obtain that t must be at least log epsilon minus log n squared divided by log of 1 minus this c of beta over n squared. And we can further simplify this a little bit by using standard inequalities on the logarithm of 1 plus x. And this would tell us an upper bound on the mixing time. So we can write this t epsilon, for example, as it's often the case. T epsilon is an upper bound on the mixing time at level epsilon. So that's the number of iterations that one must perform for the chain at this number of iteration to be less than epsilon away from stationarity. And so I refer to the lecture notes of Levin, Perez, and Wilmer to obtain more details, more precise statements for the Ising model. Chapter 15 is entirely on the Ising model and contains these results presented here as well as many others. To wrap up, we will look at a third example, the case of conditional Bernoulli distributions. So here x takes values in vectors of length n that are binary. So each component is 0 or 1, but with the constraint that the sum of the components is equal to s, a certain value between 0 and n. So for example, n divided by 2. And so the distribution of interest, the target distribution here, is the distribution of n independent Bernoullis, each with a different parameter in general, but conditioned on the sum of the x's being equal to s. So for simplicity here, we'll just assume that all the Bernoulli parameters pi are equal to the same value p in the interval 0, 1. So that simplifies things a lot. And the Markov chain under consideration operates as follows. So you have a current vector x of size n, and you sample an index I0 such that x in the set xi equal to 0. So uniformly in the set of indices I such that xi is equal to 0. And we sample I1 in the set of indices such that xi is equal to 1. To obtain a new state, we copy the current state, so x prime is equal to x, except that at location I0 we put a 1, and at location I1 we put a 0. In other words, we have swapped the entry xi0 and xi1. We have taken a 0 and a 1 in x and swapped them. And we're wondering again, how many steps do we need to perform in order for this Markov chain to be close to stationarity? And stationarity here is the uniform distribution on all those binary vectors with a given sum. We'll employ the path coupling argument again, so we'll only have to look at x tilde with distance 1 and see if we can obtain a coupling with a contraction. So x might be this sequence of zeros and ones. X tilde is another sequence of zeros and ones that is extremely similar, except that there is a minimal amount of difference, so they are adjacent. So what does it mean here? It means that there must be a place where x has a 0 and x tilde has a 1. We call that A. And there must be a place where x has a 1 and x tilde has a 0. And we call that B. And that's because, of course, the sum must be equal to S in both cases. So the distance that we can define is the half of the sum of the difference between x and x tilde. So what coupling strategy might we consider in order to obtain a contraction? Well, one of the simplest things we can consider is to try to swap the same locations in x and x tilde. That is, sample a pair of indices I0 and I tilde 0 from a maximal coupling of the uniform distributions on the set of indices such that x is equal to 0 and x tilde is equal to 0. And using a max coupling simply means we want to maximize the probability of selecting I0 equal to I tilde 0. And likewise for I1, I tilde 1, we can try to maximize the probability of selecting the same index. And then we swap on the x and on the x tilde chains. If we perform this strategy, we can compute that the expected distance over one time step, given the current states, x and x tilde, will be less than 1 minus, and then the exact rate, if I'm not mistaken, is n over 2 s times n minus s. And if we consider s to be a proportion of n, this will be approximately of the order of 1 minus 1 over n, up to a constant. So 1 minus c over n. So a conclusion from this is that we can obtain a mixing time in n log n for this swap Markov chain. So we obtain quite a precise statements about how things scale with n. But here we have assumed that all the probabilities were identical. That's it for today. In the next part of the course, we will look at couplings as a method, as an algorithmic component that we can employ to obtain guarantees on the convergence of the Markov chains without doing all the math, all the calculations that we've been doing in chapter 3. So we'll start next week on this topic. Have a nice week.